Hey everybody, we're here today talking about the vertex form of quadratic function. So to start, we'll take a look at what is the vertex of a quadratic function. Thinking about the graph, it's either represented by a minimum or a maximum. When we have a minimum, our graph is concave up, and we already know from what we've studied that the leading coefficient is going to be positive. When we have a maximum, our graph is concave down, in which case our leading coefficient is negative. Okay. Either way, it goes back to simply knowing the standard form or simply knowing the leading coefficient. Either way, concavity determines whether our vertex is a minimum or a maximum. So what else does a vertex form tell us? Well, if we have the vertex form itself, it actually tells us, well, the vertex, okay, as well as the line of symmetry. Right? Now, if we want to know the y-intercept, we could just plug in 0 here, and that's pretty easy to calculate. Let's say we want to know some general y values, okay, and solve this general equation right here. Well, not too bad. We could subtract k from both sides and divide by a and end up with x minus h quantity squared on the right-hand side. Now, when we take the square root of both sides here, okay, on the right-hand side, we end up with the absolute value of x minus h. Okay, and over here on the left side, it's some number. Okay, so it's a jumble, so some number. Okay, but what we're really looking at is that the 2 points that we're looking for, okay, they are d units away from the vertex, okay, from that line of symmetry. Okay, so that just goes back to knowing something about some absolute value. Okay, right, and that gives us our 2 solutions. And if we wanted to go even farther, we could solve for the zeros. Okay, just substituting 0 here for y and going through the process here, we could find the 0. So all of that we could find just by knowing the vertex form. But the big question is, how do we get from standard form to vertex form? Okay, now there's lots of ways, and I think I want to show one that's really straightforward. So let's say we're assuming that we know that the 2 forms exist, and we just want to verify, we just want to find the vertex. Okay, so we have our standard form on the left with f, and we have our vertex form on the right with g. So we're assuming from the beginning that f is equal to g, that they are in fact the same. Now, substituting, we get this right here. Now, in order to keep going, what I want to do is I want to keep going and expand and see what this right-hand side becomes. So I'm going to multiply x minus h by itself, okay, to get this right here. Now I'm going to distribute a on that right-hand side and get this final form right here. Now we're going to be exploiting the fact that, well, all these terms, if these two are actually the same, the quadratic term, leading coefficient, should be the same. We see it's both a. And this linear term should be the same as well, and that's the one we want to highlight, okay? Because b should be equal to negative 2a h. And if we're trying to find out what h is, that's it right there. All we have to do is divide by negative 2a, and we've got it, okay? The other thing this highlights is that the value of c is equal to ah squared plus k, okay? But we'll find a better way to find k, or a different way to find k. So finding h is as simple as finding negative b over 2a. So now we want to find k. Well, we're going to start with the fact that we know our vertex form, okay? Now, if I go ahead and plug in h into this vertex form, I want you to notice that h minus h is 0, 0 squared is 0, and 0 times a is 0. So when we plug in h here, this whole thing goes to 0, and 0 plus k equals k. Okay, so if we use this fact along with the fact that f is equal to g, all right, it tells us that f of h should be equal to g of h, right? And since we know that g of h is just equal to k, it tells us that f of h should be equal to k as well. Okay, so just to reiterate and simplify, right? When we're trying to find that vertex, all we got to do is use the fact that the h value, the x value of the vertex, is going to be negative b over 2a. And once we know that value, we can plug it back into f, see what we get, and that's going to be k. From there, we can rewrite whatever we have. So let's take a look at a couple of examples. So this first practice problem, okay, was from the unidentified flying something, right? We already know the vertex happened at 4 seconds and it was 784 feet above the ground, okay? Using what we've learned, we know the x value of our vertex should be negative b, okay? So negative 128 all over 2 times a, right? So when we plug that in, okay, we can plug this into a calculator and we get 4. Hey, there we go. Now let's say I didn't know what h of 4 was here, the value was. I could just, use my calculator, plug in 4 here and verify. In fact, we do get 784. Okay, so now that we have our values, we know a, we know h, we know k, we can rewrite this as h of t equals negative 16 times t minus 4 squared plus 784. All right, another practice problem. Okay, for f of x, it's already in vertex form, so there's lots that we already know about it. Okay, I know that the vertex is at the point 5, 4. I'm taking advantage of the transformations here, right? I also know that it's concave down. Okay, so whatever the rest might look like, the vertex is some point 5, 4. Okay, it's concave down, so I know that this represents a maximum. Okay, I could say the range is from negative infinity all the way up to 4. Okay, right? I could say that for sure. And I can also, if I wanted to find the zeros, I could. Okay, but I know that there's going to be 2, guaranteed. Okay? Now, g over here is a little more complicated. I know what the y-intercept is. I know the y-intercept is 33. Okay, great. So we got a y-intercept of 33, but it would be nice to know what the vertex is. So we can use h equals negative b over 2a. Okay, we have negative 16 over 2 times 2. Well, that's negative 16 over 4. That's negative 4. So that tells me the x-coordinate of the vertex is negative 4, somewhere over here. Now when I plug negative 4 back in, okay, and find g of negative 4, all right, we've got 2 times negative 4 squared plus 16 times negative 4 plus 33, and when you work that out, it comes out to be 1. So our vertex is at the point negative 4, 1. Okay, so we got negative 4, 1 right here. Right? I already have another point, but I know it's concave up because it's got a leading coefficient that's positive. So my graph is going to look something like this. Okay, right? I can tell you that the range is from 1 to positive infinity, and then it has no real zeros. Okay, the two solutions here are both going to be complex. All right. So I hope that helps you out. Go and take a look at the practice, and then come to some Zoom sessions and ask questions.